So we're continuing our discussion of vibrations of continuous systems, and here we're going to discuss lateral vibrations of beams. So we consider a beam with the lateral vibrations as shown here, where the beam has a length of L, a density of rho, which is a mass per unit volume, Young's modulus of E, and has a distributed load which varies in both space and time, so F is a function of x and t. Now y of x and t is the resulting lateral displacement, and we will assume that only small displacements occur. So we can draw a free body diagram, mass acceleration diagram of an infinitesimally small element of the beam. It looks like this. So on one end we've got the bending moment and the shear force, and the other end we've got the bending moment and the shear force at x plus dx, and then we've got this distributed or applied load f of x and t. And the mass acceleration diagram, we have here the mass of the element rho a dx multiplied by the vertical acceleration partial 2y by partial t squared. If we use Newton's laws and consider the rotations around the end of the beam, take the sum of the moments, the free body diagram is equal to the sum of the moments on the mass acceleration diagram. The moment is given by this bending moment, m of x plus dx, minus m of x, minus the moment caused by the shear force, v of x plus dx times dx, plus this distributed load, f of x and t dx, times, assuming it's times the kind of the half distance, so dx over 2, and that's equal to dm, which is the rho a dx, times partial 2y by partial t squared, and again that's acting in the middle of the beam, so dx over 2 is the moment arm. And if we consider a first order approximation, we can get rid of these terms, assuming that they are small. These are second order terms. So with a first order approximation, we can say that the bending moment m of x plus dx is equal to m of x plus partial m by partial x dx. The shear force v of x plus dx is equal to v of x plus partial v by partial x dx. And so our equation becomes m of x plus partial m by partial x dx minus m of x minus v of x plus partial v by partial x dx times dx equals 0. We can cancel out the m of x terms, and we get partial m by partial x dx minus v of x dx minus partial v by partial x dx times dx. Now this term we can consider as small, because if dx is small, then dx times dx is very small. So we're left with partial m by partial x dx minus v of x dx is equal to 0, and we can cancel out this dx term. And we find that partial m by partial x is equal to v of x. So basically this means that the partial derivative of the bending moment with respect to x is equal to the shear force at position x. Now if we take the forces in the vertical direction, sum of F equals ma, we have v of x minus v of x plus dx plus f of x and t dx is equal to rho a dx partial 2y by partial t squared. So we can just rearrange this slightly. So v of x minus v of x plus partial v by partial x dx. Basically we're putting in, we're writing this in this form, plus f of x and t dx is equal to rho a dx partial 2y by partial t squared. Cancel out the vx terms, and we left with minus partial v by partial x dx plus f of x and t dx is equal to rho a dx partial 2y by partial t squared. We can cancel out the dx terms, and we're left with minus partial v by partial x plus f of x and t is equal to rho a partial 2y by partial t squared. So using equation 10.23, which said that partial m by partial x is equal to v of x, we can take the derivative of that and say that partial v by partial x is equal to partial by partial x of partial m by partial x, which is equal to partial 2m by partial x squared. And now we can plug this into our previous expression, and our equation of motion becomes minus partial 2m by partial x squared plus f of x and t is equal to rho a partial 2y by partial t squared. And with small deformations, the bending moment is related to the deflection through this expression, considering the Young's modulus and the second moment of area. So m is equal to EI partial 2y by partial x squared. So now our 10.24 becomes partial 2 by partial x squared of EI partial 2y by partial x squared plus rho a partial 2y by partial t squared is equal to f of x and t. So this is the general equation for lateral vibrations of beams. But if we limit ourselves to free vibrations, so we basically are getting rid of this force term, so f of x and t is equal to 0. And if we limit ourselves to uniform beams, then that means that EI is a constant, does not vary along the length of the beam. Then we can write this as EI partial 4y by partial x to the fourth plus rho a partial 2y by partial t squared is equal to 0. Or we can rewrite this as c squared partial 4y by partial x to the fourth plus partial 2y by partial t squared is equal to 0. Where here c is equal to the square root of EI over rho a. And it's important to note that this is not the wave equation. You can look back at what the form of the wave equation is and you can see that this is not the same thing. But as with the same with cables and axial beams, we are going to look for solutions of the form y of x and t is equal to y of x times t of t. So again, we can use the separation of variables technique. And this results in partial 4y by partial x to the fourth is equal to d4y by dx to the fourth times t of t. And partial 2y by partial t squared is equal to y of x times d2t by dt squared. So our equation 10.26 then becomes c squared times d4y by dx to the fourth times t of t plus y of x times d2 t by dt squared is equal to 0. So we can separate out the x and t terms to get c squared over y of x d to the fourth y by dx to the fourth, which is equal to minus 1 over t d2t by dt squared. Now the only way that the left-hand side, which is only dependent on x, and the right-hand side, which is only dependent on t, can be equal for all times t and all positions x, is if both sides are equal to a constant, which we will call p squared. So with the left-hand side and right-hand side both equaling a constant, now we have c squared over y of x times the fourth derivative of y with respect to x is equal to p squared, and negative 1 over t times the second derivative of t with respect to time is equal to p squared. And we can rearrange this, this left-hand equation in terms of x as d4y by dx to the fourth minus beta to the fourth y of x is equal to 0. And we can rearrange this right-hand side one with just our function of time as d2t by dt squared plus p squared t of t is equal to 0. Where here beta to the fourth is equal to p squared over c squared, which is equal to rho a p squared over EI. So that p is beta L squared times the square root of EI over rho a L to the fourth. Now, this form of this equation is very familiar, and we've seen that the solution to this is t is equal to c hat sine pt plus d hat cosine pt. But now we have a form of equation that we have not seen before, so d to the fourth y by dx to the fourth minus beta to the fourth y of x is equal to 0. So to solve this, we're going to assume a solution of the form y of x is equal to g e to the sx. So the equation of motion then becomes g s to the fourth e to the sx minus beta to the fourth g e to the sx is equal to 0. We can cancel out the g's and cancel out to the e to the exponent sx, and we get s to the fourth is equal to beta to the fourth. The roots of this equation then are s1 is beta, s2 is minus beta, s3 is I beta, and s4 is minus I beta. So the total solution will be a linear combination of solutions for each of the roots. So that means that y of x is going to be g1 e to the exponent beta x plus g2 e to the minus beta x plus g3 e to the I beta x plus g4 e to the minus I beta x. Now each of these roots gi may be complex, and so we can use Euler's identity as well as hyperbolic functions to write these in a different form. So we've seen Euler's identity before, so we know that e to the I beta x can be written as cosine beta x plus I sine beta x, and e to the minus I beta x is cosine beta x minus I sine beta x. And now using these hyperbolic functions, we can say that e to the beta x is equal to hyperbolic cosine beta x plus hyperbolic sine beta x, and e to the minus beta x is hyperbolic cosine beta x minus hyperbolic sine beta x. So this allows us to write this equation 10.31 as y of x is equal to g times cos h beta x plus sine h beta x plus g2 cos h beta x minus sine h beta x plus g3 cos beta x plus I sine beta x plus g4 cos beta x minus I sine beta x. Or we can write this as c1 sine beta x plus c2 cos beta x plus c3 sine h beta x plus c4 cos h beta x, where these c's are just combinations of our g's, g1, g2, g3, and g4, as shown here. So these four constants need to be determined, and they require four boundary conditions to be specified. So typically a pair of boundary conditions are determined for each end of the beam, and this depends on the type of support. So a few common boundary conditions are shown on the following slide. So for a fixed end, we would have that the deflection at the end, so y is equal to 0, and the slope, partial y by partial x, is equal to 0. For a free end, the moment is equal to 0, so partial 2y by partial x squared, and the shear force is equal to 0, which is partial 3y by partial x cubed. And finally, for a pinned end, the deflection is equal to 0, so y is equal to 0, and the moment is equal to 0. Partial 2y by partial x squared is equal to 0. So to determine the complete response of the lateral motion of a beam, we have again found an infinite number of possible solutions which satisfy the equations of motion. So these solutions are yn of x and t is equal to yn of x times cn sine pt plus dn cosine pt, where n goes from 1 to infinity. So the total solution is a linear combination of these individual solutions. So y of x and t is equal to the sum, as n goes from n to infinity, of yn of x and t. Or y of x and t is equal to the sum, as n goes from 1 to infinity, of yn x times cn sine pt pnt plus dn cosine pt, where again this yn is like a mode shape, and this describes the harmonic motion. So the constants cn hat and dn hat are determined from the initial conditions of the beam, and we can follow the same procedure that we talked about in the previous sections. So if the initial position and velocity are specified as y of x and 0 is equal to y naught of x, and partial y by partial t of x and 0 is y dot 0 of x, then 10.34, our response gives y naught of x is equal to the sum, as n goes from 1 to infinity, of dn hat yn of x, and taking the derivative of that response equation gives us that the initial velocity y dot 0 is equal to the sum, as n goes from 1 to infinity, of pn cn hat yn of x. And using the orthogonality principle again, we can find cn hat and dn hat as shown here. So this allows us to determine the complete response of the beam when it is subject to lateral motions under a free vibration condition.